So what information do you need to be able to know when solving Voltaic cell questions? So the first thing is that they can give you different information about the reaction and expect you to figure out which reactant is undergoing oxidation and which reaction is undergoing reduction. Now it all comes back to the concept of the activity series and table 24. So you should be pretty confident at this point, or comfortable with the activity series, in that things that are higher up on the right will give electrons to things that are lower down on the left. So depending on what they specify the voltaic cell is made out of, you should be able to figure out the half equations for what is going on. If you make a voltaic cell with zinc and lead, for example, so here's the zinc half equation, here's the lead half equation. You should already know from our activity series work that zinc will oxidize and turn into zinc 2+, losing electrons, and lead 2+ will gain electrons and turn into Pb, or lead solid. The difference now is that instead of transferring the electrons directly on the surface of the zinc to the lead ions, those electrons are going to have to flow through an external circuit, an external wire. So that's the first part, figuring out the half equations. Now they could also give you the information differently. They could say that zinc is more reactive than lead. And if they tell you that, if one metal is more reactive than another, that means it's higher on the activity series. So even if that's all they gave you, you should be able to set up your own activity series with zinc and lead and their ions over here. And so you should know that zinc will turn into zinc 2+ and lead 2+ will turn into lead. And therefore the electrons must flow this way. Okay, so the first thing is figuring out the half equations. That's super important because once you know which half equation is oxidation and which one is reduction, it's going to become a lot easier to label your voltaic cell. Now, given a reaction, we need to be able to draw a voltaic cell. Voltaic cells always have two half cells. Make sure that they look like containers with some kind of liquid in them. It could just be a line across, but I like to make little squiggly liquid lines. You've got your two electrodes, which are going to be made out of metal. And you label it with wires. The wires are distinct from the metal electrodes, and you put a V on it to indicate that this is a voltmeter and that you're producing a voltage. The last bit is adding some kind of salt bridge. So it looks like some kind of tube. Let's label that one to be sure. And then we've got salt bridge. Now, depending on what they've specified, you can draw the different half equations on either side. There's no real rule about putting the oxidation on the left or the right. So you can just kind of pick whichever one you decide. But then that will determine how you draw in electron flow. So in the example that I chose above, zinc and lead, if I want to put zinc on the left, then that's made out of zinc, that electrode. This solution is made out of zinc 2+. We've got lead and lead 2+. So those are the electrodes and solutions that they're in. And okay, we'll go back to the other bits afterwards. Okay, you should be able to assign electrode polarity, meaning whether or not they are positive or negative, and also assign the terms anode and cathode. This all comes back to whether or not oxidation or reduction is occurring at that electrode. So we already determined up here that oxidation is occurring at the zinc electrode. So that's going to be really helpful, especially with our mnemonics. So von Po, we're using von. We're going to know that in a voltaic cell, oxidation is the negative electrode. So the zinc electrode has to be the negative electrode because we determined this is where oxidation is happening. We also have a mnemonic NOx, red cat. NOx, red cat tells us that the site of oxidation is always the anode. So the zinc electrode has two different ways of labeling it. We can call it the negative electrode or the anode. That means by default, the lead electrode is the positive electrode and is the cathode, because it's the site of reduction. And if we have to decide on the electron flow, we can either, once we've got the anode there and the cathode, we can use fat cat to remember that it's from anode to cathode. So electrons always flow in the external wire, that's very important. So this is outside of the voltaic cell. This is the wire that's connecting them. And this is the direction of the electron flow. From the oxidation, where the electrons are lost, they leave the battery or the voltaic cell, and they go over to the other half cell where they cause the reduction. So we can determine the electron flow. Now, the last bit is probably the least important, but talking about ion movement within this voltaic cell. Now, we saw in the half equation that zinc becomes zinc 2 plus. And we saw that lead 2 plus ions gain electrons and become lead. So a couple things I've seen is that they would describe the lead ions move towards the electrodes. That's where they gain the electrons and turn into lead. The zinc, on the other hand, starts on the electrode as zinc atoms and falls off the electrode as it gives up these electrons. So they sometimes say that the zinc ions move away from the electrodes and the lead ions move towards the electrodes. You've also got a salt bridge, and they don't usually have you go into much depth about the salt bridge, but the salt bridge contains mobile ions, so free-moving ions. They're inert. They don't play a part in the reaction itself, but they can move. And so wherever you're dumping electrons, and I can see I'm dumping electrons over into the lead electrode, positive ions will flow there. That will keep the lead half cell neutral in terms of its charge. And negative ions will flow into the zinc half cell to keep that one neutral as well. That's what the salt bridge does. So there's ion movement within the salt bridge. There's ion movement in each half cell that's slightly different, moving away, moving towards an electrode. And then there's electron movement in the external part. There's no electrons moving inside the voltaic cell, actually, except along the metal electrodes and then outside the voltaic cell in the wire. So electron flow, that's one key distinction. It's always external. And ion flow is always internal. Okay, so let's do one more practice. So if you start with magnesium is a more reactive metal than tin, what should we do with that? Well, we should make ourselves a little activity series. Put Mg above tin and put their ions over here. So I now know the reaction is going to be between Mg and Sn2 plus based on their positions. The Mg turns into Mg2 plus, gives away 2 electrons. Those electrons are going to flow around the external wire to the Sn2 plus, which is going to gain them and turn into tin. So I already know the half equations. This one is directing you to create a small activity series, which is what we just did. That's probably not going to be a direction in an actual IB question. It's just something that you should inherently know how to do. The overall balanced redox equation is the combination of the two half equations. So if the electrons cancel out, we could write the whole thing as that goes to, so it looks like a single replacement reaction, just like all the other activity series reactions. Half equations, well, I've already done that. Check it out. And draw a voltaic cell composed of these things. So I would do my beaker with electrode, my beaker with electrode, and a salt bridge. Label it as a salt bridge. If you need to pick a salt, something like potassium nitrate, sodium nitrate, potassium chloride, all options. Connect things with wires and a V box, a voltmeter. Label it completely and indicate the direction of electron flow. Well, let's mix it up and put the Mg over here, and here's its ion in the solution, here's the tin, and here's the tin ion in solution. We already know that because the magnesium is the site of oxidation, it is therefore the anode, and it is therefore the negative electrode. Again, use your mnemonics to help you. Over here, I've got reduction, therefore I've got the cathode, and I've got the positive electrode. So I've labeled them, and I know electrons flow from the anode to the cathode, so that's where the electrons are flowing. And what would happen to these electrodes over time? Well, if you look at the half equations, the Mg is going from being a solid, regular magnesium metal, to being an ion, which is aqueous. So the piece of magnesium will lose mass over time, while on the other hand, the tin ions are gaining electrons and turning into tin metal. And so over time, the tin electrode is going to gain mass.